In this lecture, we're going to discuss simplifying certain statements that are somewhat convoluted, making them more readable. All right. So we're just going to apply rules that we already have. Okay, so for the first example, we have, this is exercise 211 from the book. We have not P and Q. So what do I mean by simplifying? Well, more precisely, what I mean is find a logical statement. Find a statement that is logically equivalent to this statement, but which is less convoluted. Okay, so let's think back to our algebra of rules, and if you have to, you can always go back, but let's see, I have a negation and a bracket, and on the inside I have and. Well, maybe this is a little confusing because it's maybe not quite what you saw in the last video. So what if we said let capital P equal, right? So I'm setting it equal to not P. A little colon equal sign, that just means equal by definition. Okay, so I'm saying let big P equal not P, let big Q, let that equal Q. Okay, so then this is just the same thing as not P and Q, right? And what is this equal to? Logically equivalent to, rather. Well, in the last video, we discussed the De Morgan law, and what it says is that you can basically distribute that not through. So this is going to be not capital P or not capital Q. Okay, so now we need to rewrite the capital P as not P. So this is going to be not little p or not little q. And we already showed that not anything, you can just drop that. You can just drop the not. So you have P or not Q. And what about, well, what else is that equal to? Okay, so you don't recognize anything like this, right? But okay, here's a silly step. We're just gonna swap the order, right? Because we can certainly swap that, right? P or not Q is just not Q or P. But this is just equal to, right? This is just equal to Q implies P. Okay, so the conclusion is that the far left-hand side, not P and Q, this is just logically equal to Q implies P. Okay, so now what we would like to do is go through and justify each step. So here I'm going to write the justification. Okay, so this is our assumption, right? This is our assumption. This is a change of notation. Right? All I did was rewrite little q as big Q and not P as P. what's going on here? Well, this is the De Morgan law. One of them, at least. This is change back to notation. So change of notation again. This right here is double negation. This is where you drop your two negations. This little tail on that P, that's just how I write my P. This is the commutativity. Right, the commutativity of V, or sorry, of or, and this is just what material implication is. We gave that arrow, we gave it a few different symbols, sorry, a few different names. One was implies, one was if then, another was material implication. They're all just different names for the same thing. Okay, so that was our first example. The second one is going to be with words. Okay, so this is going to be example 2.12 from the book. So it is not true. It is not true that his mother is English or his father is French. That his mother is English. Okay, so the issue here is really when we say it is not true, what is the scope of that statement? So by scope, I mean, how do I parse? How do I parse this statement out? What is this, or another way of saying it is, what is this applied to? Well, it seems pretty clear that it's saying it like this. It is not true that his mother is English or his father is French. Another way to interpret it, and this is just the nature of ambiguity of language, is that it is not true that his mother is English or his father is French. But the reason I don't think that this is the correct way to interpret the sentence is because, remember, sort of at the beginning of the semester, we talked about the statement P is true if and only if P. It would be kind of an unusual thing to sort of make a statement, a true statement, a statement about a statement here, and here just make an ordinary statement, right? So this is about the statement. It is not true that his mother is English. And then to follow that up with, or his father is French. It just seems kind of odd. There isn't a hard and fast rule, but if you act in good faith and explain how you parse out your translation. As long as you follow all the rules, that's fine. Okay, so we're gonna let P be mother is English. Mother is English. And let Q be father is French. And so basically what this is saying is it is not the case that P or Q, and the reason this isn't simplified is because we can distribute that knot, right? So by De Morgan's law, we would say not P and not Q. In other words, his mother is not English and his father is not French. That's our final conclusion. Okay. For the next problem, we're going to simplify a few more statements. So this one is from 2.13. 2.13. This is P or Q and not P. Okay, so basically we want to reduce this as simple as possible. And we always want to explain our reasoning. Okay, so maybe this is not so obvious what to do, but look, you see a P here and you see a P there, so maybe you can combine them, right? So you go to your table and you want to see, hey, is there anything that I have where, there's something on the outside, and then I have an and then I have a couple things on the inside connected by an or. And you look at your table and you say, oh yeah, that's the distributive law. However, the way it is written is that the and statement comes first, right? So the distributive law says the following. I'll write that in a different color. So the distributive law says P and Q or R. This is logically equivalent to P and Q or P and R. And we look at this statement up here and we have to ask ourselves, are they actually the same? Of the same form? Well, they're not. So we need to put this smaller part in the front so that it looks like that. And so the first thing we're going to do is we're just going to rewrite it like this. Okay? And why is this true? Well, it's true by the commutativity. So all of these algebraic rules that we're using, you are going to have to prove that they are true at some point, or you've already proved them at this point in your homework. So the way you do that, of course, is you just show that the truth tables are equal, and if they're equal, they have to be logically equivalent. Okay, so what do we do here? Well, we look down at this and we say, okay, so here we have a P, here we have a not p. So in the last example, I guess it was 2 examples ago, I turned a not p into a capital P. We're not going to do that. We're just going to, see the general fact and keep it in mind, right? So here, what is our Q? It's a P. What is our P? It's a not P. And our R is a Q. So a lot of mismatching. But anyway, let's see. So the first thing, right, is not P. So I should write that here, right? So not P, right? And then I put an and. The second thing, that's what that is, P, close bracket, or, right, the first thing, and R, i.e. the final thing, that's Q, and this is distribution. I'm just going to write dist. What can I do? Well, I don't want to touch that yet, but looking at this is just false, right? You cannot have not P and P. That's false. So it's just going to be false. Or P and Q. So whenever I write the justification, I'm giving the reason from the previous line to the current. So what I write here is going from this step to this step, right? So what is this? This is the complement law, is what it's called. And there's a really good reason why it's called the complement law, but I don't know that I want to go into that. Okay, so what happens if you have a statement, right, and something is false and you have an or, right? It doesn't do anything, right? It's basically, it's like adding 0, right? So the truth value of this entire thing is only going to depend on this. If this is false, this whole thing is false, right? And if this is true, this whole thing is true, right? Because if at least one of these is true, the whole thing is true. And if this is false, well, that's already false. And since nothing is true, the whole thing would be false. So basically, you can forget about that false, and you rewrite that as this. And this is another complement law. Or I'm sorry, it's actually called an identity law. So this is an identity law. That's because false plays the role of an identity using algebraic language. It kind of acts like 0. Okay, and this final bit is just P implies Q, right? And this is well, we know that they're logically equivalent, or you might. I'm sorry, that's that's not correct. That would be if it was an or. So this is not P and Q. That's all you can say. It's just not P or not P and Q. Okay, so there are some supplementary problems at the end of the chapter, and I would like to go through these really quick, a few of them. Okay, so problem okay, we'll go through 2.17. This is kind of an experimental thing. Okay, so this is called the joint denial. So this is P down arrow Q, and we pronounce this neither P nor Q. So there's multiple exercises involved, actually two, and you don't need to know this for the rest of the class, but it's good to see something different, right? So neither P nor Q. So hopefully you know how to do this, even though I haven't told you what it is or how it works. So the first question is construct a truth table. So basically the idea is just using this expression neither P nor Q, we want to, motivated by how English works, we then want to determine basically when this should be true, right? So we have two variables. So let's work backward. So here's neither P nor Q, right? And I have P and I have Q, and there's two atoms, so that means there has to be 4 rows. So neither P nor Q, let's think about the words, neither P nor Q, right? Oh, what about, let's use an example. I am neither an English major, nor am I 5 years old, right? So that is a true statement because it is false that I am an English major, and it is false that I am 5 years old, right? So as an example, right, to motivate this, right, neither, actually, here we go. I am neither a English major, nor am I 5 years old. Okay, so this statement is true. And why is it true? Well, because I am not an English major. So the statement P is I am an English major. Just M for major. And then Q, I am 5 years old, right? Okay, so it is false that I'm an English major, okay? And it is false that I am 5 years old. But the statement taken as a whole, I am neither an English major nor am I 5 years old, that whole statement is true. Now clearly, if I were an English major, then I am neither an English major nor am I 5 years old? That'd be false, right? Because you could say, no, wait a minute, I'm an English major, right? So if you are an English major, then this whole statement is false because you're claiming that you're not an English major, right? And it doesn't matter. It doesn't matter what you put here, right? But um, I'll put true, right? So the point is that if I am an English major, it doesn't matter if that's true or false, right? The whole thing is false. So let's go over the other combination, right? That could be true, and this could also be false, and that would still be false, right? Because I just said it doesn't matter what this was. Okay, and then by symmetry, if this is true, it doesn't matter what p is, right? It's like saying, okay, well, if I was 5, then that statement would be true. Sorry, the whole statement would be false. A 5-year-old could not honestly say, I'm neither 5 nor an English major. Sorry, I am neither an English major nor am I 5. Okay. So we can put false here as well, and this whole thing is false. Okay, so one thing to note is that P or Q, this is logically equivalent to Q nor P, and you can immediately see that because again, if I just do this right here, right? If I just do another column, right? Based on the rule we just established here, all I do is swap the order of the columns, but that doesn't change anything, right? So this will be false, this will be false, this will be false, and this will be true, right? If I made a separate table and the only difference was that I swapped these two columns, that doesn't really change anything. So we can immediately see that those are in fact logically equivalent. Okay, so part two of this exercise says show that not P is logically equivalent to neither P nor P. Okay, so that's a really strange way to say I'm not P. So if I wanted to say I'm not a blue jay, you could oddly, it'd be kind of odd to say that you're a blue jay or not a blue jay, but you could just as well say I'm neither a blue jay nor am I a blue jay. Kind of redundant. People might look at you funny, but it does make sense. But let's prove it rigorously. So here is P. Here is neither P nor P, and here's not P. Okay, so for these to be logically equivalent, this right here has to have the same output as this. Okay, so the inputs could either be true or false. That's all there is. And well, when we did P and Q, right, those were two inputs. So, but there isn't two. So if it helps you, you can write another column with just a P, and then do true and false. Again, it seems kind of unnecessary, but so let me make my point really quick. What am I trying to say? So the table that we just had, right, only when both of these are false is this true. Otherwise, right? Otherwise, this whole thing is false. So my point here is that because both of those are p, when one of them is false, the other p is also false because it's the same one. So this will be true. And if this is true, then sort of all the p's are true, right? But if all the p's are true, then none of the p's are false, right? And as long as at least one of them is true, the whole thing is false. And in this case, one of them is true, so the whole thing is false. And here you just plainly negate, right? And since these are the same, this proves that. Okay, this next one is pretty funny. P and Q is logically equivalent to neither P nor P nor neither. So neither P nor P nor neither Q nor Q. Very, very weird. Okay, very weird. But you know, us mathematicians, we just like to do these sort of we like to find these strange identities. Okay, so this is going to be P and Q and um, P, neither P nor P. I guess I should maybe use a different color. Okay, so P, Q, neither P nor P. Neither Q nor Q. And actually, we just proved, right? We just proved that neither P, not P, is logically equivalent to P, neither P nor P. So when you look at this, right, this is how the book expressed it. Let's simplify it, right? We did this thing earlier. We talked about simplifying. This is really just the same thing as neither not P, right, nor not Q. And that's a lot easier to work with, right? So let's go ahead and do that instead. And I don't know how to erase, unfortunately. So we're just going to do not P, not Q, and then for our final part, I'm going to write that in another color because it's getting kind of all bunched up. I'm going to put the final expression in its full form, like this. Okay. And when we look at this, we'll know that these right here are that, and this right here is this, right? Okay, so how many atomic variables do we have? We have 2, so that means we have 2 to the 2 rows, i.e. 4. And here we go. Okay, so if we go through all the possibilities, you know, the usual true, 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 false, false, true, false, false. Okay, so when P is true, not P is false, and that's going to be false, and this will be false, but this will be true, and true, and false, and true, and true. Okay, very good. Now, you look at this expression and you get kind of maybe a little overwhelmed. It's a bit tricky, but just go back to your very basic rule, right? And that was the 5-year-old example I said a moment ago. And basically, it's always going to be false unless both of them are true. Sorry, unless both of them are false. So if this expression, right, if that expression is false and that expression is false, then by how we defined the down arrow, the whole thing will be true. So looking at this, you see that, okay, because this right here is this, and this right here is that, right? The only time both of them are false is right here. And so we can conclude that that's going to be true. And we said that otherwise it was false. Okay, so that is our table. Yep. Okay, so the final identity that we want to prove is that P or Q is logically equivalent to P, neither P, neither P nor Q, nor neither P nor Q. And then after I do this, I'm going to make a quick comment about sort of a philosophical consequence of all of this. And I don't like that drawing. Okay, one more time. I'm going to call this thing right here, I'm going to call it star. That way it's easier for me to draw it. That's not a logic thing, that's just a shorthand. Okay, so we have P, we have Q, we have neither P nor Q, and then we have star. And again, star is just me trying to fit that whole expression there, knowing that it's a lot to write. Okay, how many rows do we have? Well, again, we have two variables, so we have to have 4 rows. And here we go. And as usual, we're going to do it like this. So this is true, false, true, and false. Okay, so I said that neither P nor Q is true, just in case both inputs are false. So that's that right there. Otherwise, it's false. Okay, what about this last part, right? The whole expression. Well, presumably, it is only true just in case each of its parts is false, right? So neither P nor Q was true just in case P and Q were both false. So what we need is for this to be false both times here, right? So it's the same thing appearing, right? So as long as one of them is false, the other is also, because it's the same thing, is also false. Well, look, you have those all being false. So the whole thing is true, right? Just like here, those are false, so this is true. This is false, so that is true. Okay, now notice that if at least one of the inputs is true, the whole thing is false. And in this case, because one of the inputs, and therefore both, is true, but at least one is true, the whole thing is false. Okay, so that's basically it for that very weird example. But let's talk about, it's also called the joint denial, but let's think about why that would be interesting. So previously we talked about 4 different logical connectives, right? So you have not, you have and, you have or, right? And you have implies. Now implies is really just or plus negation, right? So if I had a plus b, in other words, what I'm trying to get at is, how many symbols do you need, right? So if I say a plus b, someone else can say, oh, what you really mean is not a or b, right? And you look at that and you say, oh yeah, they're the same thing, right? So if you had this list, you might ask yourself, well, how many do you need? Do I need all 4? Well, obviously not, because I can just, anytime I see that, I can just replace it. I can just replace it with this, and I haven't really lost anything. Okay, so you might ask yourself, can I do any better? And the answer is you can. All you need is that down arrow, right? Because the p, neither p nor p, that's our not, right? That's how you get not. Neither p nor p nor neither q nor q, that's our and then neither p neither p nor q nor neither p nor q, that's our or. Okay, so that's just what we showed. This isn't incredibly important, but it's interesting, I guess. Okay, and finally we're gonna do 2 more examples on simplifying. So this is problem 2.25, item I, and it says write the negation of each of the following statements as simply as possible. So he is tall but handsome. Okay, so remember, we're trying to take the negation and then we're trying to simplify it, and then yeah, that's it. We're gonna negate it and then simplify it. Okay, so we're gonna let P be he is tall. We're gonna let Q be he is handsome. Okay, so with that in mind, the first thing to do is to rewrite it. So we see the but, we're going to convert that to an and, right? So you might say, when you use but, it's kind of like a value judgment. So handsome is good. So when they say but, maybe this person doesn't like tall people for whatever reason. So regardless, if we want to make this a logical statement, this is just going to reduce to P and Q, because there's that and. And when you say he is tall and handsome, that is the same thing as saying he is tall and he is handsome. So you can put a little bracket here and write that in, he is. And that's just because, right, P and Q is true if and only if P and Q, right? They both have to be true. But keep in mind, the original assignment was to take the negation of it, right? So what is this equal to? Well, it's equal to not P or not Q. And what's the justification for this? This is the De Morgan law. So De Morgan. Okay, now we want to translate this back into plain English. So he's not tall. So you might say, you don't maybe want to say he's short. And this is where we get into the fact that not everything is true or false, right? Not everything has a strict opposite, right? So obviously there's, people that are tall, there's people that are short, and there's people that are neither, right? So yeah, it's probably better just to say he's not tall. He's not tall. And, or he's not handsome. And another way of saying this, I guess it just depends on what you consider to be the most simple. You could also say he's neither tall nor handsome. So that's that's another way of saying it. He's neither tall nor handsome. Okay, and as I promised, we're going to do one more example. So problem 4, it's kind of funny. Well, it's actually not funny. He lost his job or he did not go to work today. Okay, well, I think it's funny because someone didn't show up, and maybe it's because he just didn't feel like coming, or maybe he lost his job. But I would think if you lost your job, you also wouldn't go to work. So anyway, we're negating this. So how would we negate it? Well, again, we want to say this is let P is he lost his job. Let Q be he did not go to work today. Okay, and because of that or, right, this statement is going to be P or Q. And again, remember that we're negating the whole thing. So I'm negating this. And again, by the De Morgan law, this is going to be this right here. And what does this say? Well, he did not lose his job, right? He did not lose his, he did not lose his job, and he went. So he did not go to work today, and he did not go to work today, right? So there's a not already in there, right? And so if you negate that twice, so it's not the, so what are we not doing? We're not having not Q. That's not what we're doing. This this not is already part of Q, and then we're taking another not of that. But when you take a not here, you have to put a not around the whole thing. And if you say it's not the case he did not go to work today, that's just a fancy way of, of saying he went to work today. That's what we call the double negative in English. So in summary, he kept his job and he went to work. Okay, so that's it for this video. And in the next video, we will discuss conditional statements.